The primary physical property that we'll talk about are the boiling points. So let's take two molecules of similar size. So I've got ethanol and dimethyl ether. They're both C2H6O. So pause the video and decide which one you think is going to have a higher boiling point and which one's going to have a lower boiling point, and then come back and we'll talk about why. So the boiling point of ethanol is 78 degrees C, and the boiling point of dimethyl ether is minus 24 degrees C. So it's a difference of over 100 degrees in boiling points of two molecules that are both polar and that both have the same molecular weight. Why? It's because of hydrogen bonding. So again, this is one of the things that shows how important hydrogen bonding is and what a huge difference it makes in chemistry. Versus this one that only has dipole-dipole interactions as its strongest intermolecular force. So that one was pretty obvious. What about a primary alcohol versus a tertiary alcohol? So here's a primary alcohol, and here's a tertiary alcohol. Well, now we're within the same functional group. So now the difference in boiling points is going to be based on sterics. So less steric hindrance allows the molecules to fit closely with each other. So a primary alcohol is always going to be higher than a tertiary alcohol. And so let's take an example. So here's a tertiary alcohol. Here's a secondary alcohol. And here's a primary alcohol. So they're all C4H10O. This is N-butanol, this is sec-butanol, and T-butanol. It turns out that the boiling points are 83 degrees C, 98 degrees C, and 118 degrees C. So it's not nearly as strong of a difference because they all have hydrogen bonding. Back here, the difference between these two is that only one of them had hydrogen bonding. This one can hydrogen bond better, so it has the strongest intermolecular forces. So it has the highest boiling point, because you have to break all of those intermolecular forces to turn butanol into a gas. So we already know one reaction that we can use to make alcohols and ethers. So if I have an alkyl halide, I'll react that with hydroxide, I can get an alcohol through an SN2 reaction. This one's actually pretty good. It could do an E2 also, but primary are the worst for eliminations, so it might be a little bit better to do an SN2. We also know a similar reaction that we could use to make an ether, and that is, instead of using hydroxide, we could use something like methoxide, and the methoxide can come in and displace my bromide to make a new ether. So I've been using this methoxide and ethoxide and things like that as a base for a while. One of the things that I haven't really ever talked about is how that occurs. So I can write a reaction where I start with an alcohol and sodium hydride. The alcohol is going to be the acid, the sodium hydride is going to be the base. So I make a conjugate base of that with counter ion, plus the conjugate acid of H-, which is H2. And to think about which direction the equilibrium lies, we need to know pKa's. So the pKa of an alcohol is roughly 16, the pKa of H2 is roughly 35. So because of that, the alcohol is a stronger acid, is more likely to dissociate, and the reaction proceeds to the right. And once I have that alkoxide, I can do several things with it. One of the things that I can do with it is to make an ether out of it, just like it did in the reaction above. So I took an alkyl halide with an alkoxide to make an ether. So I could take my new alkoxide I just made and add an alkyl halide. it undergoes nucleophilic substitution to make a new ether. And what about epoxides? So the epoxide reaction is a little bit of a stretch from what we've been doing, but it follows the same idea in general. So if I have this molecule, and I treat this with some kind of a base, like sodium hydride, the sodium hydride will deprotonate the alcohol to give it a negative charge. And the reason that is because that's the most acidic proton on the molecule. All the other protons are on carbons, except for this one that's on an oxygen. It is the more electronegative atom. It can better hold a negative charge, and it's more likely to donate its proton, which means that that proton is more acidic, pK of around 16 versus a pK of around 40 or 50. Now, however, I have this intermediate that has a negative charge, and there's nowhere for that charge to go, except I also have bromide, which is a good leaving group. So if anything can come over, that leaving group can leave. So what happens is the negative charge can travel to the carbon that has the bromide on it. The bromide leaves, and it forms an epoxide. The starting material is called a halohydrin because it's got a halogen and a hydroxide on the same molecule. So it's a halohydrin. All right, so let's look at reactions of alcohols. First, they're similar to alkyl halides. And then they have a polar bond to carbon. So the C to O bond is polarized. Similarly to the C to X bond in the halogens. However, OH minus is not a good leaving group like X minus was. Remember, the halogens, the conjugate acids of them have pKa's in the -7 to -10 range. The hydroxide, the conjugate acid, is water, which has a pK of 15.74. So we're talking about even the worst halogen leaving group, which is chloride. We did chloride, bromide, and iodide. Even the chloride is 10 to the 22 times better leaving group than hydroxide. So if we take a reaction of an alcohol and react that with some kind of a nucleophile, to have the nucleophile come in and displace the hydroxide, this reaction doesn't occur because OH minus is not a good leaving group. At least not for direct substitution. So then, since organic chemists want to control everything, we don't like that very much. So what I want to do is I want to take my alcohol and somehow make it a better leaving group. And the typical way that's done is by adding acid. A lot of times we'll just write it H+. So you have to ask yourself in this reaction who has electrons and who wants them, who's the nucleophile and who's the electrophile. The proton wants electrons, so the oxygen has to be the one who has them. So electrons are going to flow from the oxygen to the proton. The oxygen gave up electrons, so that gets the positive charge now. Or you can count them, and you could say the oxygen has 1, 2, 3, 4, 5 electrons versus 6 valence electrons that oxygen has, so it's missing one, so that's a positive 1 charge. Now, if I had some kind of a nucleophile attack, and this electron pair leaves with the oxygen, now my leaving group is water. And obviously water is very stable on its own. So now this is a great leaving group.